So let's finish off by connecting the last couple of videos I did. So what does all this stuff about electrons have to do with the atomic spectra you showed me? So we had 2 videos before, one where we looked at atomic spectra, and then we took what felt like kind of this tangent off to, hey, here are electron properties, here's a bunch of numbers. Why did I do that, and how are they connected? So each line on the atomic spectra is going to represent an electron transferring from one orbital to another. When the electron absorbs energy, it becomes excited. So the electron jumps from a lower energy level to a higher energy level. You'll notice I said the word energy level. So hey, we can talk about this within our principal energy level. So we can use those quantum numbers to help determine what we should expect to happen. You may remember there was that equation for energy earlier based on N as well. So when the electron gets excited, it doesn't stay there, but instead it's going to relax back down. It's going to transition from that higher energy level where it's not stable to a lower energy level. When that happens, a common occurrence is for a photon of light to release the same amount of energy as the difference between those 2 energy levels. As an aside, in case you've already done more and you just happen to end up on this video or this class for some reason, yes, there are other ways that electrons can relax and they do other things. We're going to worry, though, about it as photon releasing, and we're just going to stick with this. We're not going to worry about like non-radiative relaxation. And if that didn't mean anything to you, that's okay. Just know photon goes from high to low, it releases a photon, we're good. Since light of different energy levels is going to have a different wavelength, we can use that color of the light that shows up in that spectrum to determine the difference between the energy levels. We can also do this with non-visible light, as long as we use an appropriate detector to determine the wavelength of light, although that's going to happen. It'll depend on the transition, what wavelengths of light we see. So, what does this look like? So, we're going to take some energy levels. And remember the first one, we're going to have smaller transitions as we go up. So at first, let's say we have an atom where the electron starts here at n equals 1. And these represent 2, 3, and 4. So first, we're going to add some energy in. Let's say it jumps from n equals 1 to n equals 4. That's our excitation. Our electron is now excited. This isn't the only way it can be excited. It can be excited at n equals 3 or n equals 2 as well, or to like n equals 5, but we're going to deal with this one. So we have the electron at n equals 4. Now, it can release its energy, and note these don't all happen with the same electron, right? The electron could choose to go from 4 to 3, or 4 to 2, or 4 to 1. And when that happens, we're going to get emission. You may notice, hey, these are different amounts of energy. So they're going to make different lines in our spectra. So the idea is you're not just exciting one electron, right? If you did that, you'd only see one line on your spectra. It would be very dim if you could somehow excite exactly one atom and have one electron jump. You wouldn't be able to see it, basically. Now, if we've got a mole of atoms instead, or even less than that, but still like a quarter of a mole or something, now a whole bunch of atoms have had one electron get excited, and they've emitted different amounts. And so those different emissions are going to show up as different lines. And that's going to be why we see differences between different spectra. Now, we're going to talk about the energy transitions to specific numerical values for hydrogen. These equations get a lot more complicated, or there's sometimes we can't solve them exactly once you get to more complicated systems. So we're going to do it as hydrogen as an example that we can work by hand rather than using a computer to help us out. Or experimentation if we can't determine it exactly. So it's possible to determine the energy of a photon released by knowing which energy levels were occupied in the hydrogen atom during an electron moving from one level to another. So we can use this equation. The energy change is going to be equal to negative 2.18 times 10 to the negative 18th joules multiplied by 1 over the final n value squared minus 1 over the initial value squared. So NF is where you ended up, and NI is where you started. You may see this equation written slightly differently. If you Google it, you could change the order of NF and NI, but then you'd also change this negative to positive. So you'll see it multiple ways. It's not a different equation, it's just some rearranging. You can also determine its wavelength. Now, you could just use the energy equation and then use E equals hc over wavelength. That'll give you the same answer. This is the faster way to do it. So you can use the equation that 1 over wavelength equals this value called R, which we call the Rydberg's constant, multiplied by 1 over NF squared minus 1 over NI squared. And here is the value for the Rydberg's constant. You'll notice this is in inverse nanometers. So if you solve this exactly, and with this equation, it would give you a value for wavelength in nanometers, not in meters. It's a good thing to keep in mind because a lot of our constants tend to be in meters. So this one, we gave you one in nanometers because that's how we're most commonly going to use it, is to find a wavelength in nanometers. So this is a pictorial representation of that. So the 4 lines that we saw that were in the visible spectrum come from the electron being at n equals 6, 5, 4, or 3, and all of those jumping down to n equals 2. Those have the right energy to make visible wavelengths. If we actually looked at the n equals 1 transition, those have more energy. They end up being ultraviolet. So we're actually seeing all the drops to n equals 2 is what we're looking at. So let's work an example of this. What does this actually look like? How do I solve a problem like this? We're going to determine the wavelength of light emitted when an electron and a hydrogen atom makes a transition from n equals 5 to n equals 3. So we have 1 over wavelength equals, I'll just write out the equation first. The Rydberg's constant, 1 over nf squared minus 1 over ni squared. So now let's plug in some things. I don't know wavelength. I'm going to leave it like that for now. I know R is 1.097 times 10 to the negative second inverse nanometers. I also know that I end up at 3, so this is 1 over 3 squared minus 1 over 5 squared. So 1/9 minus 1/25. If I do that and then multiply it by this number, I get the 1 over wavelength equals 7.80 times 10 to the negative 4th nanometers to the negative 1. This is not your final answer. This is what the inverse of wavelength is. So now we need to invert both sides. You can either think of that as I multiplied both sides by wavelength and then divided by 7.80 times 10 to the negative 4th, or you can simply do this, where we put in our calculator negative 1, which means we flip both sides at the same time. And since we're doing the same thing to both sides, it doesn't change anything. It keeps it, the equation is still true. So when we invert both sides, we'll get wavelength equals 1,282 nanometers. Now, in this problem, there was nothing to tell you a specific number of sig figs to have. So you could have said something like 1280 nanometers, and that would have been okay. N equals 5 to n equals 3 are exact numbers, so you couldn't use that. So this one, unless the problem told you, use 3 sig figs, you use 4 sig figs. Any number of significant figures here would be okay. Okay, within reason. If you told me the answer was 1,000, it doesn't tell me enough. So give me enough information I can tell what you did. Give me at least to the ones place here or the tens place. Like I would be fine with 1280. If you tell me the answer is 1,000, that doesn't really tell me that you know what it was. So with that, that's the last thing we have to do in our energy chapter. And so you'll notice this last equation, I think the hard part about this is just getting used to things being in the denominator and being able to manipulate them. I know if you haven't had to do that much, variables in the denominator can feel a little funny, but if you get some practice at this, it's not too bad. The other thing is just that you've got a lot of exponentials, not just in this, but a lot of the light problems. You have lots of times 10 to the negative something. So just more to keep track of. You also have to pay attention to your units because sometimes you're working in nanometers, sometimes meters. Sometimes you've got 1 over seconds. You have to realize it's the same thing as hertz. So working on doing things in the denominator and paying attention to your units will help you get through these problems, I think.